China's Zhang 6 lunar probe has returned to Earth, bringing with it samples from the unexplored far side of the moon.
Everyone thought the moon was just dust, rocks, and old craters, until China landed and started digging places that had not been touched before. Suddenly, new clues about lunar history began to emerge. But then, one discovery changed the entire conversation about space exploration. What exactly did China find on the moon? Join us as we uncover the secret to man's survival on the moon. The moon race. For many years, people thought the moon was well known, but that idea came from a very small piece of it. During the whole Apollo program, astronauts landed on the moon 6 times, but all of those missions covered only about 25 kilometers of surface in total. They picked landing spots near the equator, and only on smooth ground where it was easiest to touch down without crashing. The focus back then wasn't on doing the best science possible, but on picking places where people could walk and return safely to Earth. Because every Apollo landing site was chosen for safety, all of them were on the side of the moon that faces Earth, and they stayed close to the same flat regions. That meant that for decades, almost all the rocks and soil brought back to Earth came from this limited stretch of territory. Scientists learned a lot from those samples, but they were learning about one small, convenient patch of the moon, not the moon as a whole. In truth, massive areas of the moon were left unexplored and untouched by humans. There are parts of the moon that no Apollo astronaut ever saw, and because of the way Apollo was built, scientists ended up saying they know the moon. But what they really meant was that they know the safe, easy parts of the near side. Apollo was never designed to live on the moon or to explore far-off areas. Its real goal was simple: get humans there, show it could be done, and bring them back home alive. That was a moment of victory in its time, but it did not build long-term capability on the lunar surface. In contrast to that approach, China's lunar program took a very different path from the very beginning. Instead of rushing humans down fast, China started with uncrewed steps meant to build up knowledge and hardware one piece at a time. The first missions in the Chinese lunar exploration program were orbiters, satellites that went around the moon to make detailed maps of areas no one had seen up close. Those maps helped scientists put together a full picture of the moon's surface, including places that had never been touched by spacecraft. After orbiters came landers and rovers. These robots went down to the moon and began driving around, taking pictures and studying rocks and soil. One rover, called U2, traveled over the far side of the moon and sent back data about the ground there. It lasted much longer than its original mission plan, and has helped scientists learn what the moon's far side is like. That was a huge step forward in building up real experience with landing and operating machines in different lunar conditions. China then moved up the ladder to sample return missions that go down, collect real moon material, and bring it back to Earth for scientists to study in detail. Chang'e 5 was China's first successful sample return from the near side of the moon. It collected soil and rocks and brought them back to laboratories on Earth, just like Apollo did, but with modern robotic methods. This careful approach means that when China finally sends astronauts, they will be going to a place that is already well studied, where machines have laid out the path and shown what works and what doesn't. By moving step by step like this, China is putting together a much deeper understanding of what it takes to operate on the moon's surface for long periods. Instead of flying people out for just a few hours of walking and pictures, they are focusing on learning how to live with extreme temperatures, how to set up communication links, how to find and maybe use resources, and how to operate vehicles and habitats that can last months or years instead of minutes. By thinking of the moon not just as a destination, but as a stepping stone to deeper space, China's program shows a long-term vision. The infrastructure they are building, orbiters, landers, rovers, sample return systems, and communication systems, will not just serve one mission, but many future missions. Whoever builds the systems that make regular access to the moon possible will also control access to the moon, and eventually, beyond. This is a very different way of planning than the Apollo program used, and it shows that exploring space now is not just about being first, but about building up the right tools and experience over time. Now the question is, can China beat other world powers to it? The far side discoveries. For a long time, nearly 50 years, one entire half of the moon was basically a place science had never walked on or touched directly. That side of the moon, called the far side, always faces away from Earth because the moon is locked into a dance with our planet where it spins in just the right way to show us the same face all the time. When missions from the United States and the Soviet Union explored the moon in the 20th century, their spacecraft could only reach the side that faces Earth. The far side was out of sight, and for decades it stayed that way. That situation began to change when China sent its Chang'e 4 mission to the moon in January 2019. For the first time in human history, a spacecraft made its way onto the lunar far side and landed there. The mission did not just drift down randomly. Scientists and engineers carefully picked a landing zone inside the enormous South Pole Aitken Basin, one of the largest and oldest impact craters on the whole moon. The South Pole Aitken Basin is so huge that it stretches across thousands of kilometers, making it one of the most dramatic geological features in the inner solar system. It formed billions of years ago when something extremely large, perhaps a massive asteroid or protoplanet, hit the moon with great force. The impact was so powerful that it punched deep down through the lunar crust and brought up rocks from far below the surface. Scientists think that the basin exposes material that once sat deep underground, maybe even from parts of the moon's core that no human instrument had ever looked at before. The Chang'e 4 mission itself worked for about 49 hours on the far side, using a robotic arm and drills to gather surface and underground samples. But at that time, those samples stayed on the moon. They weren't sent back to Earth. Still, the mission opened up a whole new part of the moon for exploration and told scientists just how different the far side could be compared with the side we see from Earth. Years later, in 2024, China took the next step. Its Chang'e 6 mission did something that no other nation had managed before. It brought back rocks and soil from the lunar far side to Earth. The probe launched in early May, landed inside the South Pole Aitken Basin, collected material from the surface and just below it, and then blasted off again to deliver those samples back home. When the return capsule landed in northern China, it marked the first time in human history that far-side lunar material had been delivered to Earth for detailed study. In total, the Chang'e 6 mission collected almost 2 kilograms of lunar material. That may not sound like much, but it was more than enough to let scientists study the geology of the far side in ways that had never been possible before. Much of this material came from the region inside the Great Impact Basin, where the ground had been changed by unimaginable forces very early in the moon's history. Samples from this place have very unique scientific value because they carry clues about how the moon's deep interior behaved long ago. Once the samples were back on Earth, researchers began to break them down and check what they were made of. One of the first big findings was that the far side's interior behaves differently from what many older theories predicted. According to long-standing ideas about the moon's formation, the lunar mantle, the layer beneath the crust, should have cooled down quickly after the moon formed, especially on the far side. But the Chang'e 6 samples showed signs that the far side stayed hot deep inside for much longer, meaning that volcanic activity there continued later in history than scientists had expected based on earlier models. Scientists also found that the far side's source mantle, the deep material that melted to make volcanic rocks, has much lower amounts of certain elements compared with what had been found on the near side. In simple terms, this suggests that impacts and early interior processes changed that part of the moon in ways that were not predicted. These discoveries are important because they help fill in gaps in the story of how the moon formed and evolved over billions of years. Detailed analysis also showed something interesting about the moon's water. Water on the moon does not exist in rivers or lakes, but tiny quantities can be locked inside minerals. The Chang'e 6 samples revealed that the far side's deep interior appears much drier than the side facing Earth. While some earlier lunar rocks showed higher water content, the far side samples have measured much lower amounts. This tells scientists that water distribution inside the moon is not the same everywhere, and that the far side likely lost or never had as much water deep below the surface. The difference in water content and other elements between the moon's two hemispheres gives clues about what happened long ago. It may suggest that the huge impact that carved out the South Pole Aitken Basin changed not just the surface, but also the way materials were distributed deep down. Big impacts can heat up rocks so much that volatile elements, ones that evaporate easily, like water, can be pushed out into space. This could help explain why the far side looks and behaves differently from the near side. Other studies of the Chang'e 6 samples showed that volcanic activity on the far side happened in two distinct periods, one very early in the moon's history and another much later. These data also gave scientists their first direct look at how layered the moon's interior might be, including ancient magnetic characteristics that hint at a lunar dynamo, a mechanism that once generated magnetic fields. China has been able to uncover a much richer, more complex story of lunar history than was ever known before. However, there's still more to be done, and China is currently making preparations. China's bold lunar plan. For many years, China's work on the moon was mostly about exploring and finding out what's there. Its robotic missions went up to map the surface, gather samples, and send back pictures and data so scientists could study the lunar environment. That kind of exploration has helped researchers fill in gaps in human knowledge about the moon's geology and resources, but it has stayed within the realm of basic science. This early phase covered mapping, sampling, and general study missions that tested out technologies and brought back material for analysis. However, everything about China's lunar program changes direction with Chang'e 7 now scheduled to launch around 2026. This mission represents the start of a new phase, one focused not just on finding things, but on seeing what can actually be used in future human infrastructure. Unlike earlier probes that mainly took pictures and mapped the surface, this mission is equipped with instruments that will look deep into the lunar soil and environment to prospect for useful resources. Using radar and other tools, it will actively investigate how water and other volatile materials are distributed. The core aim of Chang'e 7 is to carry sensing tools designed to look below the surface, to see where water ice is buried, how deep it lies, and whether it appears in different kinds of terrain near the South Pole. These instruments include subsurface radar to peer beneath the lunar soil, drilling gear to reach down into shadowed areas, and volatile analysis tools to test what they find under the moon's harsh conditions. The mission will gather data that tells scientists not just if water exists, but how much, where exactly, and how easily it could be reached and used. This shift to looking for real, usable resources does more than add another data point to textbooks. The information from Chang'e 7 will change how engineers and planners think about living and working on the moon. Instead of just measuring ice presence in general, the mission's results will feed directly into feasibility studies for future bases. They will show whether human habitats could rely on local water for drinking, fuel, oxygen production, and other support systems, rather than hauling everything from Earth. Following Chang'e 7, China plans to launch Chang'e 8 around 2028 or 2029. And this mission moves even further past traditional exploration. Chang'e 8 is built to actually test technologies that make use of lunar materials on the moon itself. It carries devices meant to demonstrate in situ resource utilization, that is, using what's already on the lunar surface to build structures and support systems rather than bringing everything from Earth. One of the standout experiments on Chang'e 8 will involve turning lunar soil into building materials. Scientists have developed systems that concentrate sunlight using fiber optics and heat lunar regolith, the dusty ground of the moon, to around 1,400 degrees Celsius. At that temperature, the soil can melt and then be shaped using 3D printing into bricks and components that could be part of future lunar structures. This is not just a demonstration or concept model. It is meant to produce real physical objects on the moon, made from the moon's own dirt. In addition to 3D printing experiments, Chang'e 8 carries construction-capable robotics, machines that are designed to interact with the lunar surface in repeatable ways. These robots will not just watch the environment, but will move around, pick up materials, and execute tasks that resemble real construction work. This is a leap beyond past missions that deployed static instruments or simple rovers. Robots on Chang'e 8 will test how mechanical systems can prepare ground, lay down materials, and assist in building structures on a live lunar surface. China's long-term work on the moon clearly shows that the goal is not territory or symbolic victories. The approach stresses infrastructure before astronauts, systems before spectacle, and repeatable results over quick milestones. That strategy is part of a much larger vision, the International Lunar Research Station, ILRS, a project aiming for a permanent, modular presence on the moon, especially around the South Pole. More than 17 countries and international organizations, and around 50 research institutions have been connected to the ILRS plan so far. The ILRS is planned to operate both on the lunar surface and in orbit, with capabilities including transportation between Earth and the Moon, power supply, central control systems, navigation aids, and long-term scientific research facilities. This station is designed to be expandable and maintainable, with a version expected to be built by the mid-2030s and an expanded model by the following decade. It will provide paths for other nations to participate on the moon without having to build everything themselves. This is not about claiming ground. It's about building influence through infrastructure that everyone will use. In space, control does not come from planting flags. It comes from creating systems and hubs that others rely on to survive and operate. The real race has shifted from who gets there first to who builds the backbone that enables everyone else's missions. China's lunar program shows that arriving late with deep preparation often beats arriving early and leaving again. By focusing on reusable systems and groundbreaking technology testing on the moon itself, China is positioning its lunar exploration not as a tour, but as the foundation on which future space activity will be built. The real prize. Nearly every serious lunar mission planned today is aiming at the same general spot on the moon, the lunar South Pole. And that's not just a coincidence or a matter of choice. When engineers and scientists sit down and break down the physics of the moon's environment, they find the South Pole offers advantages no other part of the lunar surface can match. The moon does not have weather, an atmosphere, or oceans to move heat around. So sunlight and shadow behave very differently there than they do back on Earth, or even at the moon's equator. Up near the lunar poles, the sun never climbs high into the sky. Instead, it skims along the horizon, rising just a degree or two above it, and then slowly circling around without ever setting straight up or dipping far below. This creates a lighting pattern where certain high ridges and crater rims can stay in daylight for most of a lunar day, sometimes nearly all the time, as the sun barely moves above the horizon. That constant glint of sunlight means a reliable source of energy for solar panels and power systems, and that's something every lunar base depends on if it is to survive long stays there. At the same time, that same low angle of the sun makes certain deep crater floors stay in shadow forever. These places are called permanently shadowed regions because the sun's light never reaches them, not at any point in the lunar month. The moon's axis tilts by only about 1.5 degrees, so when the sun circles near the horizon, the shadows in these deep bowls never lift. With no atmosphere to warm them up, temperatures in these craters can get down to hundreds of degrees below zero, colder than the surface of Pluto in some cases. Those permanently shadowed regions act like giant cold traps. When water molecules, released by comet impacts, micrometeorites, or solar wind interactions, drift into these shadowed depths, they freeze instantly and stay frozen. There is no heat, no sunlight, and nothing to make water ice evaporate back into space. Over billions of years, ice built up in these craters and likely stayed there ever since, stored in near-eternal darkness. Because of this, scientists think the South Pole holds some of the most promising deposits of lunar water ice anywhere on the moon. This dual pattern, sunlit highlands and shadowed ice traps side by side, is exactly what lunar explorers are looking for. Near the equator, a lunar day lasts about 2 Earth weeks, followed by a lunar night of the same length. During that long night, solar power systems go dark and temperatures plunge, so landers and rovers have to power down or put up with extreme cold. But at the South Pole, some ridges receive continuous sunlight that can keep solar power systems running almost all the time. Meanwhile, just a few meters away are craters where water ice could be captured for use. This mix of power and resources right next to each other is precisely why countries are converging on the South Pole with their missions. China is directing its robotic landers and orbiters toward this area to map, sample, and hunt for ice, just as NASA's Artemis program is choosing landing zones in this region for human explorers. Neither nation is simply copying the other. Instead, they are responding to the same physical realities that make the South Pole uniquely valuable for both scientific study and future living possibilities. Volatiles, including water ice, are important because they could be turned into breathable oxygen, clean drinking water, and even rocket fuel. If future explorers can pull up water from the lunar ground instead of hauling it from Earth, it would be a massive reduction in cost and risk for long-term projects on the moon and beyond. That's why missions like NASA's Viper rover plan to explore water ice near the South Pole, and China's upcoming Chang'e robotic landers are both zeroing in on this same area. NASA's robotic missions, including the Lunar Reconnaissance Orbiter and the ShadowCam instrument flying with Korea's Danyuri orbiter, are giving scientists detailed pictures of what the South Pole region actually looks like. They put together visual maps showing sunlit ridges and deep-shadowed floors, letting planners see exactly where permanent darkness lies and where near-constant sunlight shine. By combining multiple datasets, researchers can build up a comprehensive terrain map that helps guide where landers might touch down and where rovers might roam around once they're on the surface. ShadowCam's images are particularly important because the camera can see into the darkest parts of the South Pole that traditional lunar cameras couldn't image before. These detailed pictures highlight the deep shadows inside craters like Shackleton and others near the pole, giving scientists an unprecedented view of the terrain that is likely to hold ice deposits and that will be critical for planning exploration activities. As a result, lunar South Pole exploration is not just about seeing another part of a familiar satellite. The common focus on this region unites diverse missions and international programs, not because of politics or rivalry, but because the laws of physics and the natural layout of the moon's terrain push everyone toward the same places. When you remove atmosphere and weather, what you're left with is a landscape defined by how sunlight falls and how shadow traps ice, and that landscape points clearly to the South Pole as the next frontier for lunar exploration and use. Do you think humans would be able to live on the moon in the future? Let us know your views in the comments. If you enjoyed this video, like and subscribe to this channel. Before you go, watch the other videos on your screen.